Heterocycles are rings that contain at least one atom other than carbon. This is a vast category of organic molecules, and some of them meet the criteria for aromaticity. Pyridine is a nitrogen-containing analog of benzene. It is a ring with a p orbital on each and every atom. It must also be planar due to its small size and the sp2 hybridization of the ring atoms. Furthermore, it has 6 pi electrons in its 3 pi bonds, which is a 4n plus 2 value. We therefore expect pyridine to be unusually stable, and in fact it is. However, we fail to consider the role of the lone pair of electrons when analyzing pyridine. Although it will not alter our conclusion in this case, it will impact the decision for many heterocycles. So let's establish the lone pair's relationship to the pi system. The nitrogen atom in pyridine is sp2 hybridized. The 3 sp2 hybrid orbitals are used in nitrogen's 2 sigma bonds, as well as to house its lone pair of electrons. Since the lone pair is housed in an sp2 hybrid orbital, it is orthogonal, or 90 degrees to the pi system. Only the node of the sp2 hybrid orbital overlaps with the p orbital on nitrogen, and nodes are points of 0 electron density. Therefore, the lone pair of electrons is not a part of the pi system in this molecule. It does not overlap with the pi system and cannot contribute to it in any way. As a result, we were right to ignore the lone pair when counting pyridine's pi electrons. However, this will not always be the case. To illustrate the point, let's consider pyrrole. The structure of pyrrole is shown in the upper right-hand corner of this slide. Much as with the cyclopentadienyl anion, it is initially unclear whether or not there is a p orbital on every atom of the ring. Before we knew about resonance, we would have simply considered the nitrogen atom to be sp3 hybridized. But we now know that pyrrole is actually a hybrid of its 5 resonance forms. And in 4 of those 5 resonance structures, the nitrogen atom is sp2 hybridized. This shows that there is indeed significant p orbital character on each and every ring atom. If the nitrogen atom were merely sp3 hybridized, as we would have concluded prior to learning about resonance, the electron pair repulsion would be minimized, but the lone pair would also be isolated on the nitrogen atom. By adopting sp2 hybridization and placing the lone pair in an unhybridized p orbital, these electrons are made a part of the pi system, which allows them to be delocalized over the entire ring and stabilized as a result. Having shown that pyrrole contains a continuous cyclic array of parallel p orbitals, we have also illustrated that the lone pair is a part of the pi system and must therefore be counted when we tally the pi electrons. Pyrrole has 4 pi electrons in its 2 pi bonds, as well as 2 additional pi electrons in the lone pair. The total of 6 pi electrons is a 4n plus 2 value, meaning that pyrrole is also an aromatic molecule. When comparing the examples of pyridine and pyrrole, it becomes apparent that the lone pair electrons may or may not be a part of the pi system. This must be decided on a case-by-case basis. We can generalize, though, conditions leading to each conclusion. If the atom bearing the lone pair is participating in a pi bond, it already has a p orbital in the plane of the pi system and could not, therefore, donate the lone pair to the pi system. Such was the case with pyridine, as shown on this slide. On the other hand, if the atom bearing the lone pair is not participating in a pi bond, then it can contribute the lone pair to the pi system by placing it in a p orbital parallel to the others. Such was the case with pyrrole, as shown on this slide. The situation is further complicated by heterocycles that possess atoms with more than one lone pair, such as furan. Now we have to decide whether oxygen will contribute 0, 1, or 2 lone pairs to the pi system. We can use the generalized guidelines that we just developed a couple slides ago. Oxygen is not participating in a pi bond. Therefore, it can place one lone pair into a p orbital that overlaps with the rest of the pi system. However, it would not be possible for oxygen to contribute the second lone pair to the pi system. One lone pair can occupy oxygen's only p orbital that is parallel to the pi system. Oxygen simply does not have access to a second p orbital in the valence shell in the same plane. Therefore, the second lone pair resides in an sp2 hybrid orbital, shown here in purple, which is orthogonal to the pi system. As a result, furan contains a total of only 6 electrons in its pi system. There are 4 pi electrons in the 2 pi bonds, and there are 2 additional pi electrons contributed by one of the lone pairs. The total of 6 pi electrons is a 4n plus 2 value, illustrating that furan is an aromatic molecule as well. To summarize, when counting pi electrons, if the atom bearing the lone pair or lone pairs is participating in a pi bond, it cannot donate any lone pair electrons to the pi system. However, if the atom bearing the lone pair or lone pairs is not participating in a pi bond, it can donate one and only one lone pair to the pi system.